Okay, you guys, so we've been talking about how you can find the area under a curve. We've talked about how that has meaning, right? Especially when this a velocity function and how that area actually represents your displacement. That means how much the object moved and also which way the object moved by a certain amount, you know. So the question is this: why is it we still can't find area under a curve without that calculator's help? That's kind of troublesome. We should be able to do it by now, you'd think, right? Okay, so here's the question of the day. How do we find area without technology, right? So how do we find something like the area under 3x squared without a calculator? Okay, so you guys have a handout, so you don't have to follow my notes exactly. But let's just talk about this in general. So let's say that you were given a random function. This is not 3x squared, but it's just a random function. Something looks like this. Okay? And let's say that you wanted to collect area. We'll just start at 0 for this demonstration. Let's say you start at 0, and you want to start getting area. Okay, so you're going to go to the right, and you're going to pick like a value of x, maybe right here. And you just want to look at how much area you've collected. I would say so far we've collected a small positive area. Right, please pay attention. Please pay attention. Thank you. So far we've collected a small positive area, right? I don't know how much, but it's definitely positive because it's above the axis. So we'll just call this value A. So let's say we just found, I don't know, 1 square unit of area. Okay? And then just for the sake of argument, let's say that this is the point 5 and this is the point 8 on the x-axis. Okay? So we've maybe reached x equals 1 and we've collected a little bit of area. Maybe 1 square unit or half a square unit, something like that. Okay, we definitely collect a little area. If you go out a little further, let's say to x equals 2 maybe. Let's say over here, you've collected a little more area, right? Still positive, we've gained a little more area. If you go out to x equals 3, you've gained more area still. X equals 4, you've gained more area. X equals 5, you've gained area, right? And so what's happening is the area is increasing. So let's try and keep track of the area now. So we started with no area at all, right? And then we started gaining area like this, right? Until we got to x equals 5. Now you might think, something interesting is going to happen now. You know, we just reached x equals 5, so something interesting is going to happen. The function is starting to come back down, but isn't it true that if you keep collecting area, let's say you go to 6, 7, and eventually 8, you've been collecting area this whole time, right? So nothing really interesting happened at x equals 5. Turns out you're just not collecting areas quickly when you go past 5. You're collecting smaller amounts of area, but you're still gaining area. In other words, this graph just keeps on rising. We're gaining area, we're gaining area, we're gaining area all the way to 8. Okay, now I doubt that's a straight line. You know, so I'm just showing that I gained area. I don't think it's straight though. Okay, now what happens if you go past 8? So back to the first picture there. If you go past 8, let's say you go out to 9, what just happened? You just gained area, but it's what kind of area? Negative area. So it's going to cancel out some of the area that you've achieved so far there in red, see? So that purple area is going to cancel out some of that red area. So the graph, basically what we're saying is the area function is going to start falling off. We just lost a little area. See that? And if you go even further out, so x equals 10 or something, you've lost more area still. Okay, so what we're looking at down here in the second picture is the area, or you could say the integral from 0 to x of f of x dx. This is just the function f up here. The second one is like a different function. It's the area under f of x. And it too is a function. It changes, you know, depending on how far out you want to go. If you go all the way out here to x equals 5, you collect another. It's changing all the time, the amount of area as we traverse across. So this is also is a function. And it's typical not to have x in the upper limit and also in the integrand and have x as your integration variable. In other words, it's pretty common we don't really want this to be an x and this to be an x and this to be an x. We don't want that. So typically you'll see that people will change this then to some other letter. So like t is very common. Don't let this throw you off, okay? They just don't want to have x in the upper limit and also in the integram. So we call this a dummy variable. I mentioned it on Friday. Just change it whatever you want. Don't try to have x up in the top and the bottom. So that right there represents the amount of area collected as x continues. Okay? But something interesting pops out at me when I look at this. Where have we seen this kind of behavior before? Let's put the phones away, pay attention, okay? Otherwise you run the risk of memorizing calculus and not understanding it. So where have we seen this kind of behavior before where the peak on one graph represents the root on the other graph? We've seen this before. This is what happens when one graph is the derivative of the other, right? Isn't it true that when a graph reaches a relative maximum, the derivative graph will pass from positive to negative? So this isn't a proof, but it sure looks like f of x there, that first graph, is actually the derivative of that second graph. Does that make sense? In other words, the second graph is the antiderivative of the first graph. We've seen this behavior before where the peak relative max here shows up as a root, specifically going from positive to negative. We've seen this behavior before. This is the derivative graph. Of this. Very interesting. Yes?
How do you get a quadratic graph from deriving linear?
It's not linear. Like I was saying, I was just kind of roughly sketching. This actually is not a linear. It's actually more curved. Okay? I didn't curve it while I was teaching it because I wouldn't see if you would see why it was curved, but the area actually grows slowly until you get to certain spots and faster certain spots. So this is not perfectly straight. The point was it was rising and then it was falling when we passed through this root because we started losing area, so it dropped off. And this appears to be a function, and this appears to be its derivative. Okay, so that's not a proof of any kind, but it seems that area then has something to do with anti-differentiation. Is your hand up? You have a question? Okay. All right, so that's just like a little like clue, you know. And so on your paper there, let's just take the assumption to be true that the derivative of the area function, so this was the 0 to x f of t dt. Let's give this a name. A lot of people call this capital A for area, okay? But you can also just simply call it capital F. Capital F means the antiderivative of lowercase f, okay? Where F means triple equal sign is defined as. So F is defined as, sorry, I meant to write df dx, the derivative of it is f. So in other words, it's like an antiderivative. The derivative of the area function is the original f. Okay, so let's start off with this statement here. df dx is the area under the curve. Let me write this, just basically what I have in your notes there. df dx would be d dx of, I'm going to try and show you that this actually works, the area from any value of x to x of f of t dt. This is just the same statement I said a minute ago. That this is f of x. The derivative of the area function is the original function. And we know that if you do an antiderivative, right, you have to be careful. I'll show you why. Because if you do, let's say that I gave you a problem like this one, and I say, okay guys, I'd like you to guess the antiderivative of 3x squared. So what is the antiderivative of 3x squared? Yeah, can you think of a function whose derivative is 3x squared? X cubed. Okay, that's true. So if this is f, capital F would be x cubed. The problem with this is that's not the only possible answer. Yeah, isn't it true that you could have like a plus 1 million here? And this still has the derivative 3x squared, isn't that true? Okay, so when you come up with an antiderivative, just know that there's always this plus unknown constant. Okay, there should be any number we want there. In other words, one function has an infinite number of antiderivatives. Of x cubed plus 1 is an antiderivative of 3x squared. X cubed plus 100 is an antiderivative of 3x squared, and so forth. Okay, so there's this ambiguity. So it's probably just safest to write something like this. The integral from any value a to x represents the antiderivative, but there could be a c here, like a positive constant or a negative constant even, that we don't know yet. Any number will go there, actually. We don't even need to find it always. But let's say that you wanted to plug in just a for x. What would happen? This is sort of an interesting scenario. If you plug in a for x, what is the area between a and a under a curve? 0. Right. So you can see in this very unusual case that f of a is negative c, or you could say c is negative f of a is another way to write that. So we can go back to this statement at the top, here in purple, and we can update it, writing it like this. The integral from a to x under a curve is f of x minus f of a. And this is a very, very, very famous rule right here. If you didn't follow the derivation for it completely, that's okay. It wasn't a formal derivation, it was just a rough idea. But you can see that this is a brand new formula, so to speak, and this is called the fundamental theorem of calculus. And you'll see it in the book written like this. The integral from a to b of f of x dx is f of b minus f of a. Okay? So let's try doing this problem that we've been wondering about for so long. Some of you already knew how to do this. Maybe you learned it from Ms. Fusco. Let's just evaluate the following areas. This time we're not going to use a calculator. And I know Aaron already knows how to do this. Did you learn it from physics class or just figured it out? All right, very good. If you're trying to integrate from 5 to 10, let's say, 3x squared, geometrically this is what it means. You have the function 3x squared, right? And between 5 and 10, it rises a lot. We want that area. We've been answering questions like this for a while, but we've needed the calculator. Watch how easy it is. What is the function whose derivative is 3x squared? X cubed plus c, right? So you would first write down x cubed plus c, not 3. This is the function whose derivative is x squared. And then you would plug in these two numbers, 5 and 10. Okay, so we write that by putting 5 at the bottom and 10 at the top like this. But it just means plug in 10 and plug in 5 and then subtract. Okay, so it's going to be like this. 10 cubed, which is 1,000 actually. So it's going to be 1,000 plus c minus, and then you're going to plug in the 5, 125 plus c. And the c's actually cancel, and you just get 875. Now if you turn on your calculator and you type math 9, 5 to 10, 3x squared, dx, you will see it says 875. But we did it without a calculator. And we're going to do some more. Does it work? Some of you are typing it in? Okay, very cool. All right, so what we're going to do is do this next one now. And we're going to put our limits of integration right here. Okay, all I need from you is, and don't forget the plus c, but I need to know what function has a derivative cosine. Sine. Sine is the function whose derivative is cosine. So I'm going to put sine of x plus c here, and I'm going to plug in pi over 2 and 0 and subtract. So you don't need brackets anymore. They just kind of turn into parentheses. Let me just finish this example real quick. So I've got sine of pi over 2 plus c minus sine of 0 plus c. What is sine of pi over 2? 1. What's sine of 0? The c's always cancel. If you want to stop writing the c's altogether, you can for a definite integral. So the area right in here is 1. That red area has value 1 is what we're saying. Pretty cool. Okay, and let's go ahead and do that last example there. So the last example that I had in your notes, same type of problem. We have integral from -1 to 1, 1 over 1 plus x squared dx. So you might recognize that this is just the derivative of arctan. So we're going to do arctan of x plus c from -1 to 1. So we're going to be doing arctan of 1 plus c minus, and then arctan of -1 plus c. And this gives us pi over 4 plus c minus negative pi over 4 plus c. In other words, pi over 2. And you'll notice that the c's always cancel out, so when you're doing a definite integral, like I said a moment ago, just feel free not to even use the plus c. And that's the answer. All right, so our summary today is you can find the area under a curve from A to B, or area between the curve and the x-axis from A to B, if you can evaluate what the antiderivative is, and then plug in B and A, and take the difference between them. We'll talk more about some details of that later.